Module 11. Now let's talk about the histology of compact bone. Out of the two types of bone tissue, compact bone is the strongest. And as the strongest, it's going to offer a lot of protection, especially to the weaker spongy bone and red bone marrow found within the core of most of your bones. Also, as the strongest bone tissue, this is the bone that's going to offer the most support for the body, meaning it has the ability to uphold your body weight, which is why if you think about your long bone anatomy, it's the shaft of the long bone that's going to have to uphold that body weight and resist all of that pressure. And what type of bone tissue forms that shaft, that diaphysis? You're right, compact bone. Also, compact bone is really great at resisting stress and resisting fracturing made by weight and movement. However, only when the stress arrives in a limited range of directions. This particular type of tissue cannot withstand fracturing if the stress comes from multiple different directions. So this bone is really good at resisting stress, but only when the stress is coming from one or just a few directions. And all of this is due to the anatomical organization of the compact bone. With regards to structures, the first structure I want to mention is something called a perforating canal. The perforating canal is a channel that passes from the surface of the bone, penetrates in through the bone matrix, and connects to your functional unit, your osteon, specifically a part of it called a central canal. Now, what this perforating canal does is it brings into your bone tissue blood vessels, nerve endings, and lymphatic vessels. So it's bringing your blood supply into your bone. It's bringing nerve endings into your bone. The next structure I want to mention is your osteon, which, as was mentioned in the last module, is the structural unit of your compact bone, and it's what looks like that tree trunk in the histology slides that you saw in lab. Now, anatomically speaking, osteons contain two distinct structures. The center of the tree trunk is an opening called the central canal. And the central canal is going to run the entire length of your osteon. And the central canal is filled with blood vessels, nerve endings, and lymphatic vessels. So it's going to help to pass those structures through the bone matrix. The growth rings on the tree trunks, which look roughly circular, are called your concentric lamellae. Recall that a lamella is a layer of bone matrix. Now, you learned in the previous module that the bone matrix is composed of inorganic mineral salts, but also organic material such as collagen protein. And what they have found is that the collagen protein is very highly organized within each of these bone layers. If you look at the lamellae that have been separated out for you in the artist drawing, you can see that the collagen is actually in a helical organization, meaning the collagen actually spirals along the length of the osteon. I've had students say that this resembles the threads on a screw, but I've also had students say it looks like the stripes on a candy cane or on old-fashioned barbershop poles. You have that spiral. I've even had someone say it looks like the DNA spiral. Now, this spiraling of collagen actually is different in different areas of the compact bone. They have found that the collagen is more loosely coiled in areas of the bone that resist bending forces, and more tightly coiled in areas that are more weight-bearing. So depending on the types of stress that are on the compact bone, the collagen organization can vary. They also found that the collagen in each of the lamellae alternates in direction. So if you look at the drawing, you can see in the outer layer the collagen sort of winding to the right, but in the next layer in it's winding to the left. And this alternation of direction actually increases the strength of your osteon, much like how alternating the wood grains in plywood strengthens plywood. Now, if you try to conceptualize what an osteon really looks like, and it is sometimes very difficult from these artistic drawings, even though they do try to make it look a little more three-dimensional, an osteon is a cylinder. So it's going to be extremely long and round. So in your head, envision a paper towel roll, toilet paper roll, and if you have that cylinder and start thinking about how the collagen is spiraling along the length of that cylinder, your osteons are extremely strong along their length, really, really strong along their length. However, they are very weak in their width. So with regards to the strength of an osteon, if stress is applied to the cylinder along its length, that cylinder will not fracture. However, if you apply stress along any other axis, for example, transversely across that osteon, it will fracture. So osteons are strong along their length, very weak along their width. So remember when I said, with regards to compact bone, that they do resist stress and fracture, but only if the stress comes from a limited range of directions. That is because of the osteons and the fact that they're strong along their length and very weak in their width. Now, because of this, your osteons tend to be aligned in directions of stress. So let's take your diaphysis. With the best that I could muster in PowerPoint, the center structure is your femur. You have the two epiphyses, the broad ends, and then you have the diaphysis running down the center. So I'm talking about the middle structure. If you were to look at the diaphysis and look at the osteons, I have a blue cylinder drawn to the left-hand side of that shaft. All of the osteons in the diaphysis run parallel to that shaft. So they're all running straight up and down the shaft. The reason for that is if you consider the stress applied to that shaft, the stresses run from epiphysis to epiphysis. So the normal stress line for that shaft is straight up and down. If the stress is running from end to end, your osteons are all aligned in that precise direction of stress so that they can resist fracture. However, if you apply stress coming in transversely, so coming in from the side, you're going to hit that shaft at its weakest spot because you're going to be hitting all of the osteons in their weakest direction, which is why getting hit a blow to the leg from the side more easily results in fracture than an increase in stress along its length. Also, I do want to mention that osteon organization can actually change if you change the stress on the bone. Now, granted, it takes a little bit of time for the osteon organization to change, but if you were to start going to, if you were a couch potato and then you started going to the gym, and you had all types of different stress being applied to your bone surfaces, your bone is going to have to change in order to make sure that it doesn't fracture when you are doing all of that exercising. So this organization can change if stress changes. All right, your next histological structure I want to mention are things called interstitial lamellae. Interstitial lamellae basically fill in the spaces in between your osteons. Now, it is believed that these interstitial lamellae in compact bone are remnants of older osteons that got remodeled when new stresses were applied to the bone and new osteons were formed. The last structures I want to mention actually extend around your outer and inner circumferences. I like to think of them as little finishing layers, and they're called circumferential lamellae. So you have outer circumferential lamellae that are going around the outer circumference of your bone, and you have inner circumferential lamellae that are going along the inside surface of the bone. So your circumferential lamellae run parallel to your bone surface, and again sort of form that finishing layer on the outer surfaces. Okay. Now that you've learned a little bit about the histology of compact bone, let's look at the histology of spongy bone. Spongy bone is usually found in areas that are not heavily stressed. Again, spongy bone is the weaker of the two types of bone tissue. So if you have a bone that's made mostly out of spongy bone, you're not going to put it in an extremely weight-bearing area. Also, you'll find more spongy bone in areas where the stresses actually come from multiple directions. Spongy bone, with regards to function, actually has the ability to withstand stress and fracturing when stress comes in multiple directions, and the reason it can do this is its anatomical structure. The trabeculae and the spicules are small bony plates and little bony spikes, and you can actually arrange these plates and spikes in multiple directions all at the same time. So you can have your trabeculae in these multiple directions of stress, allowing the bone to resist fracturing no matter how the stress is actually applied. Now, if you think about long bone anatomy, this ability is reflected in the anatomy. Your epiphyses, the part of the bone that is actually at the joint, is primarily made out of spongy bone with only a thin layer of compact bone on the outer surface. Having spongy bone at the joint allows the epiphyses to resist fracturing when you have those multiple directions of stress. Spongy bone also makes your bones a lot lighter, and lighter bones are going to be easier to move and to support with your skeletal muscles. Now, even though spongy bone is the weaker of the two bones, it can offer some protection to the red and yellow bone marrow within it. Please remember that the red bone marrow is going to be in areas like your flat bones, such as the bones of the skull, your ribs, your sternum, your irregular bones, your vertebrae and your coxals, also the proximal epiphyses of your humerus and femur. Those are your big red bone marrow areas. Now, histologically, if you were to look at the trabeculae and take a look at their anatomy, the trabeculae do have layers of bone matrix. They are considered to be interstitial lamellae. You have lacunae, canaliculi, you have osteocytes living in those canaliculi, you have osteogenic cells on the outer surface. You have osteoblasts on the surfaces. You have osteoclasts on the surfaces. So all of that is very similar to compact bone. The trabeculae, like osteons, are oriented along lines of stress. And what is really interesting is that there are no blood vessels actually penetrating into the trabeculae, which was different than in compact bone. In compact bone, you had perforating canals with blood vessels, you had central canals passing blood vessels, but you don't have it here. And the reason is that your osteocytes, because these trabeculae are so thin, your osteocytes are not very far away from your bone marrow, meaning that the osteocytes can actually absorb by diffusion what they need from the bone marrow. Both red and yellow bone marrow have really good blood supplies. So your little osteocytes can actually just absorb by diffusion everything they need from the tissue surrounding them. All right, so now that you know about the structure of your two types of bone tissue, let's talk about how you form it. So we're going to go in utero. We're going to talk a little bit about osteogenesis. Now, osteogenesis is the birth of bone, and that's the term that I'll be using. However, you might see in some books that they refer to this early bone formation process as ossification. However, just to ease confusion, we're going to stick with osteogenesis. Now, osteogenesis actually begins with a really soft embryonic tissue called mesenchyme. Mesenchyme is a loose, fibrous connective tissue that actually forms many different structures in the embryo. It forms bone, it forms cartilage, it forms muscle. However, we're going to be referring to how we use mesenchyme to form bone in this chapter. Now, bone formation begins around the 6th to 7th week of development, and this mesenchyme is going to be converted into bone through one of two methods. One is called intramembranous ossification, and the other is called endochondral ossification. Now, if you go in the lecture textbook, there is a lot of detail added about these two processes. However, after discussions with our nursing program years ago, we discovered that these details are not necessary to help support our students' success in those programs. What is going to support your success is more of a conceptual, overall knowledge of the two processes, which is what we're going to do. Now, intramembranous ossification involves bone forming directly in and from mesenchyme. And this type of ossification occurs in the deep layers of the dermis, which is sometimes why this bone is referred to as dermal bone. Now, at the end of intramembranous ossification, the bone that forms has spongy bone in its center, bordered by compact bone on its outer surfaces. And the bones that form this way are the flat bones of your skull, part of your clavicle, your mandible, the bone that replaces your fontanelles, those lovely soft spots in the infant's skull, and there is a role for intramembranous ossification in bone widening. Now, endochondral ossification forms all of the other bones. So you could say endochondral ossification forms most of the bones in your fetus, and it's actually a two-step process. Your first step is to change mesenchyme into hyaline cartilage. This hyaline cartilage is then going to be replaced by bone. So this particular method of ossification has a middle step that intramembranous ossification does not. Now, with regards to the steps involved, again, we're going to keep this very conceptual. The first step is going to be the formation of what is called a cartilage model. So that means we're going to have to take mesenchyme, this generic loose fibrous embryonic connective tissue, and actually change it into something that can actually be called cartilage. So I want you to imagine that we form this little nugget of cartilage. You can use the far left image to kind of visualize it. And you're going to have a little nugget of cartilage matrix. Inside that matrix, you have your most abundant cartilage cell called a chondrocyte. And those chondrocytes are in little lacunae, little lakes, because the cells have to live in water. Around the outside of the cartilage nugget, you have a membrane called the perichondrium. Very similar to the periosteum, except it surrounds cartilage. In the perichondrium, you have chondrogenic cells. So you have cells that will reproduce, very similar to osteogenic cells. And when chondrogenic cells divide, they put chondroblasts on the surface of the cartilage. So you've got chondrocytes living on the inside of the cartilage nugget, and you have chondrogenic and chondroblasts living on the outside of the nugget. However, it's this little teeny tiny nugget of cartilage. And what we need to do is we have to grow that nugget so that we have a cartilage model that looks like the bone that we are going to form. So basically, you want to have a little teeny cartilage femur, a little teeny cartilage rib, a little teeny cartilage humerus. You want your bones, you want this cartilage model to resemble the bones. So in order to grow your nugget, we're going to use two different types of growth. The first type of growth is called interstitial growth. Now, interstitial growth is sometimes nicknamed growth from within. So that means we're going to grow using the cells that are on the inside of that nugget, meaning we're going to be using our chondrocytes. Now, chondrocytes are different from osteocytes. Remember, osteocytes were the maintenance men. They didn't build a brand new matrix. They couldn't reproduce. All they did is maintain the matrix that was already there. Chondrocytes don't do that. Chondrocytes have the ability to make new matrix, and they have the ability to reproduce. So when you do interstitial growth, you're going to be using those chondrocytes to make your cartilage grow from the inside. And this particular type of growth causes bone lengthening to occur. So interstitial growth is going to make your cartilage longer, which is why you have an epiphyseal plate in your metaphysis, because chondrocytes have the ability to do interstitial growth and cause lengthening. Osteocytes do not. Bone tissue on its own cannot lengthen because osteocytes cannot do interstitial growth. So this is something very, very unique about the cartilage. Now, if you're making your nugget longer, you also have to make your nugget wider. And to widen your nugget, you're going to do something called appositional growth. Appositional growth is growth on your outside surface. So we're going to use chondroblasts on the outside of the nugget to add new layers to our outer surface. And by adding new layer after new layer to your outer surface, your nugget's going to get wider with every layer you add on. Now, at the end of all of this growth, we're going to have this really nice cartilage model, and what we need to do then is convert this cartilage model into bone. and form, a diaphysis and an epiphysis and a marrow cavity. Now, all that is remaining of your cartilage model at birth and into your mature life are the epiphyseal plates. The epiphyseal plates that you have in your long bones up to and including puberty are remnants of this cartilage model. Also, the articular cartilage that you have at all of your movable joints throughout the entire human body, all of that articular cartilage is leftover cartilage model from your fetal development. And again, this articular cartilage is needed because it helps to cushion the ends of your bones at joints, it reduces friction, it absorbs shock to protect the bone that's underneath. But again, it's all that's left of that little cartilage model you formed as a fetus. All right, so now imagine you've been born and you have a skeleton. Your skeleton has undergone intramembranous ossification, endochondral ossification. You've got an actual femur and humerus and ribs and everything. However, you're 20 inches long, 22 inches long, and how tall are you now? So clearly your bones were not done growing the moment you were born. So what we need to talk about now is how does bone continue to grow after birth? And bone is going to have to grow two ways. We're going to have to lengthen and we're going to have to widen. Now we're going to talk about bone lengthening first. And bone lengthening is going to involve interstitial growth at the epiphyseal plate. Now, the reason we're going to use that epiphyseal plate up to and including puberty is because cartilage can use interstitial growth and lengthen. Your chondrocytes have the ability to reproduce and to make new matrix. Bone tissue can't. Osteocytes lack the ability to do interstitial growth. They can't divide and make new matrix. Now, if you look at your epiphyseal plate, it actually has various regions to it. Very generally speaking, your epiphyseal plate has hyaline cartilage in its center. So in the middle of the plate, you've got hyaline cartilage. And on either side of that epiphyseal plate, you have what is called a transitional zone. Now, the hyaline cartilage in the center of the epiphyseal plate undergoes continual interstitial growth. The growth inside this plate is going to create the growth in length because as the cartilage expands, it's going to push the epiphysis farther away from your diaphysis. Now, if that was all that happened, you would end up with these huge wedges of cartilage developing in the metaphysis, and that doesn't happen. In fact, your epiphyseal plate during your growth periods never changes in overall thickness because of the transitional zones. The older cartilage in the transitional zones actually becomes calcified, meaning you start to deposit the hydroxyapatite crystals in it, and then this calcified cartilage is changed over into spongy bone. And this changeover into spongy bone is going to help you extend your epiphysis and your diaphysis. Of course, on the diaphysis side, the spongy bone would then be changed into compact bone to make sure that you have a nice strong shaft of compact bone. Now, after puberty and you're done growing, all of the cartilage is replaced by bone. Normally, the loss of the epiphyseal plate occurs between ages 18 to 25, But again, that's just an average range. It could happen earlier, it could happen a little bit later. The reason that you lose the cartilage is that the chondrocytes that are in the epiphyseal plate, they get old. They get tired, they stop functioning, and the chondrocytes basically stop dividing. So the cartilage itself stops lengthening. Also at the exact same time, you're going to start to see an increase in bone growth due to the sex hormones that you're producing, in addition to thyroid hormone, growth hormone that you have as well. And what ends up happening is that this drastic increase in bone growth at puberty actually overtakes the cartilage, completely converting it into bone. Which is why after puberty, all you have in the metaphysis is an epiphyseal line. It basically indicates to your physician that the cartilage is gone and lengthening can no longer occur anymore in that bone. Now, if you lose the epiphyseal plate too early, you could end up with bones that are too short. So if a small child actually falls and has a fracture in an epiphyseal plate, you'll actually see the physician periodically do x-rays of the arm while it's in the cast, or the leg, whatever was broken, to kind of monitor the health of the epiphyseal plate. One really great way to have your cartilage stop growing and encourage that overtaking of bone growth is to actually physically damage it. So you could end up with a child where one bone doesn't grow for the appropriate amount of time, and now you have a child with one arm shorter than the other, one leg shorter than the other. So damage to the epiphyseal plate isn't really something that you want to happen. It needs something that does need to be monitored if it does occur. Now, as your bones are growing in length, you have to remember that your body mass is increasing. So you've got more muscle mass, your other organs are getting bigger. So you don't want your bones to get longer, you want them to get wider so that they're stronger and can support that increase in body mass. So you also have to grow in thickness. You have to grow in width. And appositional growth can be done by bone, because appositional growth occurs due to intramembranous ossification on the outer surfaces of your bone. And if you think back to the previous module, on your outer surfaces, you do have osteogenic cells giving birth to osteoblasts. So you do have bone builders on the outside surface capable of performing appositional growth. These osteoblasts are going to lay down matrix on the surface of the bone and just start adding new and new layers of matrix parallel to your bone surface. Now, all of these layers are going to form circumferential lamellae. So imagine, just putting on a t-shirt and then a sweater and then a jacket and then another jacket. You keep adding layer after layer and you get wider and wider and wider. Now, as this diameter is increasing, you are going to use osteoclasts on the end osteal surface, so on the inside of the bone, to actually dissolve away matrix and help widen your marrow cavities in those diaphyses.